This is Deirdre Scholar from Geography at Cabrillo College. This podcast is about humidity. The amount of water vapor in the air is referred to as humidity. Most atmospheric moisture occurs as water vapor rather than liquid precipitation or snow that's solid or ice that's solid. Water vapor is colorless. We can't see it, it's odorless, and has no taste. We are not normally aware of the amount of water vapor present in the atmosphere unless there are very high levels of humidity. Then we can tell it is there because our skin may feel sticky, objects may feel damp. We may also notice when water vapor content is very low because our skin, our eyes, and nose may feel dry and chapped. When water vapor condenses, clouds, fog, rain, snow, sleet, etc. will form. Then we can see that moisture. It is much more conspicuous. Water in the vapor state plays a huge role in atmospheric processes, particularly in its ability to store heat, thereby making it easy for winds to transfer that heat around the planet. Humidity also plays a big role in the development of wildland fires. As humidity levels increase, this factor can help firefighters trying to control or extinguish wildfires. As humidity levels drop, fires are much harder to control. In this podcast, we will learn about factors controlling the amount of water vapor present in the atmosphere and how to calculate humidity levels. Let's begin with how water vapor enters the atmosphere, which is mainly through evaporation from bodies of water such as the oceans, rivers, lakes, streams, etc. Water vapor also enters the atmosphere through evapotranspiration. That would be moisture evaporating out of soils, rocks, and vegetation. The rate of evaporation, or evapotranspiration, in other words, how quickly or slowly moisture gets into the atmosphere, is affected by how warm or cool the air is, what the temperature of the water is that's being evaporated, if there is wind or if it is very calm and still, and how much humidity is already in the air. Is the air humid or is the air dry? People who dry their clothes outside are very aware of how quickly or slowly those clothes dry. So therefore, they're very much in tune with the rate of evaporation. So if you hang your clothes out to dry on a warm day with plenty of wind and low humidity levels, the clothes are going to dry very quickly. If you hang the clothes out on a day where the air temperature may be warm, but there's no wind and it's already quite humid, the clothes are going to take a very long time, may not actually even dry at all. Most of California has warm air, we do have winds, and we have pretty low humidity levels. So most of California has ideal locations for drying clothes outside using the natural sun energy. Cooling air can bring unsaturated air to its saturation point. So this is what we refer to as condensation. So condensation is the opposite of evaporation. This is when water vapor in the gas state converts or turns into liquid water, actual droplets that we can see. Most of the time, condensation occurs when the air temperature cools below what we call its dew point. The dew point is the temperature at which air reaches its saturation. So let's talk about saturation. This saturation curve helps to explain the relationship between air temperature and humidity levels. First, let's orient ourselves with the graph. We have temperature on the x-axis getting warmer to the right and colder to the left. And on the vertical y-axis, we have grams of water vapor per cubic meter of air. So in other words, how much water vapor is contained within the air at different temperatures. The red line, or the red curve here, is what we refer to as the water vapor capacity. So it means how much water vapor can air at different temperatures actually hold in that vapor state before it condenses. Let's just look at an example. If the air temperature is 100 degrees Fahrenheit, 38 degrees C, the water vapor capacity, in order to determine what the water vapor capacity is, we would come straight up from that temperature until we hit the red curve, and then we would use a ruler to go over to the vertical axis and determine the number of grams of water. So it looks like for 100 degree Fahrenheit air, we hit that red curve about here, maybe just a little over 35, so something like 36 grams of water vapor can be held in that vapor state in that air before it would condense. If we look at air temperature of maybe 30 degrees, how much moisture can be held, how much water vapor can be held in that air? Notice that here we hit that red line very, very quickly. And going over to determine the number of grams, it looks something like maybe 5 grams of water vapor using the saturation curve there. So can you fill these two sentences out? Warm air and its capacity for water vapor versus cold air and its capacity for water vapor. So warm air has a high capacity for water vapor. In other words, warmer air can hold a lot more moisture before it hits that red curve. Cold air has much lower capacity to hold water in the vapor state before it condenses. There are a few different ways of expressing humidity. The most commonly used is relative humidity, which tells us how close the air is to its saturation with water vapor. As we remember from a previous slide, when we see droplets of water, maybe on our car, maybe on our grass, maybe on patio furniture in the morning and it hasn't rained, we might ask ourselves, well, how did that condensation occur? And relative humidity helps to explain that. Let's look at a graph of a 24-hour period of time. So we have time down here on the x-axis, starting with midnight, going to midday, and then ending with midnight. We also have temperature on the left vertical axis, and we have relative humidity on the right vertical axis. So let's first focus on temperature and the red line, which represents the changes that occur with temperature throughout the day. So at midnight, we actually haven't reached our coldest temperatures. The temperature continues to drop until just before the sunrise. And after sunrise, the temperature warms. It doesn't actually typically peak at noontime. It typically peaks sometime after noon. In this graph, we're seeing about 4 p.m. is the peak of the temperature of the day, the high temperature. And then after about 4 o'clock, it tapers off and cools off again. How is relative humidity change as a function of that? Well, at midnight, as the temperature cools up until sunrise, relative humidity actually continues to increase and climb. Then as the temperature increases, and when it peaks at that sort of 4 p.m. time, relative humidity continues to drop off. So relative humidity gets very, very low when temperature is very high. And relative humidity gets very high when temperature is at its coolest point of the day. This is a very typical pattern that happens, and this helps to explain why when we go outside in the morning, maybe to get the paper off the front lawn or the driveway, it's wet because relative humidity has climbed so high that water has reached that condensation point, that dew point temperature, and we now have water vapor condensing onto surfaces in our front garden. So on these couple of sentences for your notes, as temperature increases, what happens to relative humidity? So here we have temperature increasing. What's happening to relative humidity? And as temperature decreases, over here, what happens to relative humidity? So I'd like you to be able to fill in those sentences and make a statement that as temperature increases, here, relative humidity decreases. And as temperature decreases here, relative humidity increases. So we call this an inverse relationship because as one function rises, the other drops, or as the other drops, the other one rises. So an inverse relationship between temperature and relative humidity. Now let's do some math with relative humidity. Relative humidity can actually be calculated, and I'd like us to practice a few examples together. First, the equation, relative humidity, which I will abbreviate RH, is equal to the actual amount of water vapor in the air divided by the capacity for air at that specific temperature to hold moisture in the vapor state. And because relative humidity is always expressed as a percentage, we are going to multiply that by 100 to bring it into a percent. Capacity is not something that you'll know off the top of your head or even be given in these examples, but you will need to use the saturation curve to determine the capacity. We did that prior. We looked at what's the capacity for air at 100 degrees Fahrenheit or 38 degrees C, and we went up to the curve till we hit the curve, and I think we determined about 36 grams. So that would be the capacity if we knew our air temperature was at this level. Okay, so our first example is that 1 cubic meter of air has a temperature of 16 degrees C, which is 60 degrees Fahrenheit, and contains 7 grams of water vapor. What is the relative humidity? So we're actually being given the actual amount of water vapor in the air. It's telling us that it contains 7 grams. So that's going to go in the top here in the numerator of the equation. But now we also need the capacity. And again, there's nothing in this example about capacity, but it does tell us what the temperature of the air is, 16 degrees C. So let's use our saturation curve here. We're going to find the temperature of 16 degrees C. We're going to come straight up until we hit the curve, the red line, the water vapor capacity, and then we'll have to use a straight edge to make sure we are as accurate as we can be to get over here to determine the actual amount, the capacity amount of that temperature air to hold water vapor. So from that, I'm thinking this is a capacity of 14 grams because 15 grams would be like halfway and it's not quite there. So we have our 7 grams, our actual amount, 14 grams is the capacity based on the saturation curve. And again, we have to crunch these numbers. We have 7 divided by 14 is 0.5, multiply that by 100. So our relative humidity in this example is 50%. This next example, we're warming the air. So if the air temperature in the previous example warms to 27 degrees C, which is about 80 degrees Fahrenheit, and the water vapor content remains the same, what is the new relative humidity? So now we still have 7 grams, but our capacity has changed. Let's see what happens to capacity. So it's warmed to 27, so here we are at 80 degrees Fahrenheit. Again, we come straight up. It's a little more than 20. To me, that looks like it's about 21 grams, so I put 21 grams in there. And doing the math here, we get 0.33, multiply that by 100. So the relative humidity now is dropped from 50% to 33% just by warming the air. By changing the air temperature, relative humidity has changed. The final example here is if the air temperature cools now to 4 degrees C, 40 degrees Fahrenheit, again, the water vapor content remains the same, but what is the new relative humidity? So 40 degrees C coming up here looks like it's right about 7 grams is the capacity. So 7 over 7 is 1. So we are now at 100% relative humidity, and condensation will indeed be occurring. We may actually get precipitation as well. The final thing to mention here with respect to humidity is that it can influence how a given temperature feels to us, and we call this sensible temperature. On a warm, humid day, the air seems hotter. We would say that sensible temperature is high. This is because air is near saturation, and any perspiration on our skin is not going to evaporate easily, and therefore will not cool us off. Because of course, when moisture evaporates off of our skin, that cools us down. So the air seems warmer than it actually is. On a warm, dry day, there is very good evaporative cooling taking place. So the temperature doesn't seem as hot as it is in the case when the relative humidity is very high. So do be aware that we can have two temperatures exactly the same, maybe 85-degree temperature on the East Coast in the summertime, 85-degree temperature in Santa Cruz in the summertime, but the relative humidity, if you have 95, 98% relative humidity in New York City and 85-degree temperature, it's going to feel so much hotter than if you have 85-degree temperature and 20% relative humidity on the West Coast. Okay, that concludes our podcast on humidity. Thanks for watching.